Hi, everyone. I'm Patrick McFadin. I work in developer relations at DataStax, and I'm also an Apache Cassandra committer. And I'm here to talk to you today about a petabyte scale vector store for generative AI. Now, before we get started, let's talk about the big elephant in the room. This is probably you right now. You're probably feeling a bit stressed out or behind. And of course, everyone has a boss that's asking like, hey, when do we get that AI? Because that's a big deal, right? Everybody's talking about it. When's ours? Let's all take a minute and relax. Because the main reason we worry about, what's happening in the future is because of FOMO. And that's okay. Everybody's dealing with that fear of missing out. But we're all learning together right now. So I just want to level set and say, not everyone's got this figured out. There's probably like 5 people in the world who have it figured out, and they all work at like OpenAI. Don't worry. We're all learning together. So as you learn things, share as a community. And I'm here to share some of the things I've learned. So with that said, let's get into it. So there are 3 things for success that I want to talk about around storing vector data and working with generative AI. First is that simple. Keep it simple. I've built really complex data infrastructure in the past. I do not want to do it again. So neither should you. Simple is perfect because that means you can move fast and get things done and not worry about it. Second is a thing that is probably more prevalent with generative AI, and that's privacy and security. You want things to be private because you're probably looking at your own data, and there's a lot of really good information in there that somebody would like to see that you don't want them to see. Keep it private and secure. And then finally is that performance for the low price. Generative AI infrastructure is probably the most expensive thing you can run in your infrastructure. It's just costly because you need things like GPUs. Well, how can you get the most performance for the lowest price? And that is more important than ever. And granted, working with data is not generally a cheap option, but at this point, even a little bit is a lot. So let's look at that. So where are we going as a community? And I think that's a really good question right now, because where we're going, where we've been, it's moving really fast. And you need to start thinking about what's happening in the future. I want to talk about this a bit. Agents are an interesting future for what we're doing today with generative AI. Andre did this great talk. There's a link in here. You can check it out, the QR code. He gave this little inspirational speech at this hackathon. He's basically like, hey, I know we're working on chatbots today and we're doing modeling and all those other things in LLMs, but really agents are the interesting thing. I would always encourage you to go out and look at what's next, but the things that are happening in LangChain and Llama Index and with LLMs are very much geared around agents. So pay attention to that. And those agents are going to need something really important. They're going to need these large-scale agent networks, which are loosely connected, dynamic, and then that shared context. Everybody's going to be talking to each other, and they're going to want to know what each one knows. And that those agents are going to have context. Agents without context, what do we call that? Siri? I don't know what you said just a few minutes ago. Okay, well, the context is that shared memory that when I tell you something, I think that's a really cool part of like ChatGPT. I'll ask it a question or I'll give it some data and it'll analyze it, but then it'll come back with an answer, and then you can ask it to, oh, well, can you add this or do that? It has context. It knows what we were talking about. It's not every new query is new. It is that there's like some background to that. Cool. Well, agents are going to need that kind of large scale context at a massive scale. So let me tell you about Cassandra and how that fits in here. This is what Cassandra was built to do. So when Cassandra developers started seeing what was happening in Gen AI, we got a little excited. The people working on the project, because we've been working on a distributed database that works at an incredible scale, at global scale, meaning that you can run it anywhere and everywhere in the world. And it works at a highly distributed way as well. We built this thing 12 years ago. We've been perfecting it over the time. It's a really baked and really good database. It runs probably everything you can think of in the world right now. Banks, healthcare, insurance. It even runs, if you're running an iPhone, it's pretty much running that. So it's great. Now with Gen AI, we're super excited because we got more to do. And why because we've built a system that will help power that invincible brain, the memory, that large scale memory, because it is shared nothing, linear scale, and fully replicated. And how are we going to do that? Well, worldwide. And that's what Cassandra really does well. We're really excited because this is the thing we built, is this massive global scale cluster of a single cluster, one set of data that can span the entire planet. So far, we've only tested it on Earth. We're going to work on testing it beyond Earth once we get the capacity to do that. But I'm fully sure, I am absolutely confident that we're going to make that work. So the 5 problems that we're currently solving, hard problems we're currently solving around Gen AI, are around vector search. And so vector search has these 5 that we want to address, like the scale out capabilities. That's something we've already built into Cassandra. Go team. Garbage collection is not probably more traditional, like garbage collection in Java or something like that. It's similar, which is whenever you create indexes and then you update them, how do you get rid of the old stuff? And we work with highly transactional systems. So we think about indexes as something that's somewhat transient. They will be updated all the time. What if you have a very transactional system that is doing 1 million writes per second and doing a lot of updates? Well, that will build up quickly. So how do you prune out that obsolete index information? First of all, so it doesn't cause the wrong answer. And second of all, so it doesn't load up your infrastructure with a whole bunch of extra stuff. Not good. Now, we also want to think about, speaking of loading up with a lot of extra stuff, that effective use of disk. Indexes tend to use a lot of disk, and we don't want to be the one that's blowing out your infrastructure. It will, when you start getting into petabyte scales, prepare yourself. That is a lot of infrastructure. You just need a bunch. But we want to be really efficient with throughput and make sure that the data that's stored on disk, which is the source of truth, is enabled for high throughput. And then the composability. Vector search is a type of search, but there are many of them that you still need to use. What if you want to use an exact term, like exactly this? Like you could say equals, or a like term where maybe it's just a little more fuzzy. And then full on ANN search, like approximate nearest neighbor. Like all 3 of those things should be available and should be in the same place. That is what we call hybrid search. That's very contextual. And then the big one for us is concurrency. Most vector databases or vector indexing schemes were built around the idea that there would be some job, like a Spark job or something like that, that would create a bunch of indexes from data. You would take the model, create the vectors, store them on disk, and then some other system would come along later and index them. And then those indexes would be read many, many times. So we have a write once, read many. Okay, that is a great use case. And that was probably when NLP and some, like when we were doing indexing of pictures, like on Facebook, that sort of thing. Sure. But now we're talking about transactional systems. Now concurrency is a thing. We're going to be reading and writing data, and we need it available instantly. That's a problem we solved a long time ago with Cassandra. Now we're solving it with vector search in Cassandra. And one of the ways we're doing that is with a library called JVector. And JVector is really sweet because it's, first of all, Java, we wrote Cassandra in Java. It's a Java project. However, there's not a lot of Java projects that have to do with generative AI, especially on the infrastructure side. A lot of it's in Python, a lot of it's in C++. But JVector is a pure Java version of a vector indexing scheme. And it is really fast, and it is really popular. It was one of the top trending repositories for a few days on GitHub, just because people are like, oh, this is what I want to use, because I use Java with my programs or whatever I run in my infrastructure. This is going to be a library I can use for that. So caught a bunch of tailwind on that. But it's very, very modern. It uses Panama, which is a new API that's available in the latest versions of the JVM. So it's fast. And that's what's powering the Cassandra search, the vector search and indexing on the back end. And we proved it out. So if you look at Pinecone as an example, which is built on indexing, like I said before, write once, read many, we tested it against the JVector against that, and what we found was that is you're reading data and then you start the writes, that's the thing you want to measure, because when you start doing that, if you're using a system that isn't ready for concurrency, the read latency will just shoot through the roof and your throughput will drop as well. And that's not good. You don't want that in a system that you're using for, say, an application, and like a mobile application or a front-end application. It just isn't going to work for you. So this is something that we're solving. And it seems like this is a problem with every single vector database we've run into, is this concurrency problem. And we're really excited that this is being solved, because it's one of the problems we've been solving for a long time in Cassandra for a while. And same with MongoDB Atlas here, same thing. And as a matter of fact, as we look at others out there that are using, say, the Lucene HNSW or something like that, or HNSW Lib, they all seem to have the same problem. And which is, that is a thing, and I'm sure they will solve it eventually, but that's something we solved today, and we're just going to continue to solve more throughput problems. Our goal, again, back to the topic here, is we fully expect this to be a petabyte store for vectors. Why? Well, let's talk about that. Because these generative AI apps that are being built today are going to scale. And so what we're thinking about is, like, what is it going to take for you to be okay? And when I say okay, meaning that you don't feel like tomorrow or the next year that you are going to feel like you made a bad choice. We want you to use this database today so you can use it tomorrow and the next day, and probably until the end of your application lifecycle. And that's something that Cassandra has been doing for a long time. There are clusters out there that have been up for more than 10 years. I am not kidding you. So we think long term, but we also don't want you to have to switch around your data. So thinking about how does that happen? We need it to be responsive. It needs to be cheap or low cost. I'm sorry. Has to be fast, right? That's the thing. It's like the more throughput, the lower cost it's going to be overall. And it's going to give you a better budget for your application. And then that security I mentioned earlier, when we built this into Astra, our Astra database as a service, which is Cassandra behind the scenes. Part of that, of running it as a service, is going through all the security and compliance. And right now with LLMs, all the worry around LLMs and the privacy, and hey, can I put healthcare data in there? We have HIPAA. Can I use financial data? PCI, SOC 2, ISO 27K. All of those things are hard. It takes years for you to get it right and to go through the certification. We've got that. So again, click a button, it's good to go. So those vector use cases, like what's going to happen, I mentioned before, it's going to be agents, but there's a general pattern for all the use cases when it comes to vectors. So I wanted to start by talking about LLMs, and LLMs have some great things. And this is really what started this, right? Is when ChatGPT jumped on the scene and said, hey, look, you can chat with this thing and it's using this LLM, which is massive. GPT 3, 3.5, and now 4, it just blew everyone's mind, because inside of the LLM was some really cool stuff. And primarily it was around communication, is when you could have natural language communication with something and it could respond back with a sentence instead of just giving you like a blurb of text, or you had to use a certain syntax. No, you could be kind of fuzzy and it would figure things out. So it did communication and reasoning, which is really interesting. The reasoning part was kind of a surprise. Like, hey, give me all the steps to do this thing. And it would reason through those steps. It was much more than just a parrot where you give it some words and it would kick out the response. It actually did some thinking in there. I hate to use the word thinking, but that's kind of what we saw, and that's when everyone had their AGI panic. It's like, oh, is GPT-4 a brain? Probably not, but it's just really good because of the way that it is designed to do that reasoning task. The thing that it's really not good at is knowing things. And the reason being is that there's a certain amount of training data that was created and used, and then the LLM was created using that. Well, that training data is the extent of its knowledge. And what LLMs are really good at, and we have a good laugh about it, is giving you a very, very confident answer that is completely wrong. And then we call that hallucinations, of course. But we've learned I think we've learned enough. There's been some funny stories about lawyers like submitting briefs with the absolute fallacies built into it because they asked ChatGPT for some background. We learned, all right? We all learned. But how do we get there? And there's talk about using LLMs in ways that probably are not fit for purpose. And that would be like, oh, let's bake as much knowledge as possible in an LLM. Probably not the right thing, but we do want to have the right kind of knowledge for the communication and reasoning that we want to pull out of it. But how do we get rid of this whole hallucination thing? Because when we build AI agents, we're going to want the source of truth. The last thing you want is an autonomous agent to wander off with some wrong notion. And let's say that you have an agent that's like planning your vacation and it plans a vacation on the moon, which isn't possible right now. Well, maybe it can make it up. Well, and then you all of a sudden you're paying like $100,000 for a rocket ride that will never get you to the moon. Bad hallucination, especially if you're giving it your credit card. You do not want hallucinations. So the way we think about this is AI agents have two parts to be successful. They interact with LLMs and they use a vector database for that source of truth, like that knowledge, the brain, like your memory. So if you think like how humans work, we can process language, but then we have our memories as a backstop to make sure that the things that we say are based in some sort of truth. At least some people do that, but regardless, it isn't like we're randomly spouting off things. Like we know things, like whenever we have context between two people or some topic. And multimodal memory will be the way to make that work best for agents. And right now we do a lot of text, we do some video, some images. The new ChatGPT thing with the images is really cool. This is just a hint of what's coming, and there's going to be more. But multimodal, I don't think anyone would argue, is the direction everything is going. And multi-modes means multi-data, and then multi-data means we're going to have a lot of things to process, create a vector and embedding, and store so that we can get a much bigger picture. And this is an example of a paper that was going into this like universal multimodal learning, and like X-rays, what? Hyperspectrum, not just text, not just audio, not just image, infrared, time series data. Like you think about like that is all the things that we're going to need to make good decisions. All right, that multimodal data is out there. And what's going to happen when we have that? It's going to explode. There's going to be so much data out there. When it comes to data, you can always count on there being way more than you expect. 100%. This is a graph from November of 2019 or 2018 saying, hey, we expect by 2025, it'll be 175 zettabytes. Wow, what's a zettabyte? I don't even care anymore because I think that's not going to even be true anymore, especially with proliferation of LLMs and all the vector data. It's just going to get bigger. And a lot of that's going to be machine generated. It's going to be a lot of information that's going to be generated, stored, used, not just human information, but even human information, things like your chat history or just watching a video. Video is a really big thing. What if you broke down the video into multiple parts? Now you're just multiplying out all that data. I guess the point I'm making is it's really easy to make this argument. We're going to need a lot of data, and it will happen to you. So when this is this typical pattern for that data, so when we create vector embeddings, generative AI apps are using this kind of pattern. And this is the one I was showing you earlier, where we have these autonomous agents that make calls to both an LLM and an embedding model. So the user's asking for something, it's combined with the user, with the embedding model, and then sent to the LLM, reasoned through, and then eventually sent back to the LLM for that final response or reasoning for the user. This is what was called RAG, or Retrieval-Augmented Generation. It is the pattern. If you haven't heard of it, welcome. If you've heard of it, you probably heard about it a lot, because this is the dominant pattern right now for reducing hallucinations, but also working with LLMs with your user data. When you hear people say, I want to chat with my data, they're probably doing some form of this. Things like the libraries like LangChain and LlamaIndex both use this pattern to reduce the amount of hallucinations, but also give it a much faster and more, and dare I say, cheaper response, because embedding data into a vector database is a lot less costly than trying to create a brand new LLM with all that data in it. That's a very expensive proposition. So you combine these two things, maybe even cache the responses, cache the prompts, it gets low cost really quickly. And that key to being fast and efficient is this RAG, right? Like, and the embeddings or that vector that's being stored, this is why fast vector search is such a big deal for us. It's 10 times faster than Lucene. So you got to be quick, and it'll probably get faster. And the relevancy, you have latency, you have throughput, but you also have relevancy with vectors. And relevancy is how accurate are those responses or close to what I was looking for. The more relevancy, the better, but it gets harder as the data gets larger. That's something we're always going after. And then just being able to handle data at scale, at these massive scales, is really a trick. And it's something that we've been building at DataStax for a long time. We know how to run Cassandra at scale. And at scale, you can run it pretty low cost. We could probably run it at half the cost of anybody right now because we've learned all the efficiencies to make it work. But we're always going to get better at that. Cost of cloud should go down over time and not up. And when you think about who's actually using this, it's like, wow, I mean, this is an actual thing. Priceline has this thing in beta called Penny, and it's out there. This is one of the people that uses our vector search on Astra right now. It's or one of the companies, and you can see like this is no small company, and they've got a lot of things, and they've got some really cool stuff. But their chat app is all about, hey, tell me about the property I'm in, context. And it gives back a good response that's relevant. The last thing you want is for this thing to start wandering off. Yeah, like, tell me, how can I help you today? Well, that's the first time in New York, and it starts telling you about Philadelphia. I don't want to know about Philadelphia. So you can do this today. You can follow this link, and you can sign up. It's pretty easy. If you don't have a vector database running within 5 minutes, call me. I will help you out. It'll be less than 5 minutes, trust me. And that's the thing. You can download this, run it on Cassandra open source. It's out there. But to get to do it today, click a button. It's really easy. And so we have our vector search that's built into it. You can create a database and get working today. There's Colab notebooks if you want to start working on it. And we work with startups. We work with projects. We want to help you. Remember back when I said this is an everybody problem? Everyone feels behind and is trying to catch up because their boss is asking them to do this tomorrow. Well, or yesterday. We are there for you. We have a bunch of programs where we can give you free credits, consulting. We're just trying to help you get there faster. So I'll see you at the AI.dev and at the Cassandra Summit on December 12th and 13th. That's pretty soon. Follow me on LinkedIn. I'd love to connect with folks as well, and I hope to see you there. Thank you.